So we've talked about Bode plots previously, and now I want to talk a little bit more about how to relate that to circuits and how to understand what they do as easily as possible. So if we had a circuit like this, as you know, with two impedances, call them Z1 and Z2 in series, and we just want to know the voltage across this guy as a function of the voltage across this guy. The current that flows around this thing is V sub I divided by the sum of the two impedances, Z sub 1 plus Z sub 2, and then V out is equal to that current flowing just in Z2. So if I want the ratio of those two things by voltage division, we just use that. So we have a series impedances and a voltage divider between those. We can do this. Now, if we made Z2 out of a capacitor, then this becomes easy to do and forms a so-called low-pass circuit. So if we put a capacitor C here, the impedance associated with the capacitor, let's talk about is 1 over the admittance associated with the capacitor. The admittance of the capacitor is SC, and the impedance is 1 over SC. So if we just plug into this where Z2 is 1 over SC, using the voltage divider formula, 1 over SC, and the impedance of this guy, let's make it be a simple resistor, call it R, then this thing forms, as we'll see, a so-called low-pass circuit. And you can already tell we can rearrange this a little bit. Let's multiply top and bottom by SC. This becomes 1 over SCR plus 1. And you can tell by looking at this, based on the techniques we used for Bode plots before, if S equals J omega and and omega is real small, this term goes away and this whole thing approaches just 1. So this thing has, we would say, has a DC gain of 1. If S equals J omega and the magnitude of this term, omega, is real large for real high frequencies, the 1 goes away and this overall thing is inversely proportional to frequency. So sometimes we might write this in sort of filter form, H0 divided by 1 plus S over omega naught, where we'd say H0 in this case is the DC gain, or passband gain. In this case it's equal to 1 because of this, just matching it up. And omega 0 is called the cutoff frequency. There's various other names for it. This is the radian frequency. So there's an F0, which is omega naught over 2 pi. So this would be in hertz. And the cutoff frequency in this case is omega naught is just 1 over RC. All right? And based on what we've seen before, we can make an asymptotic Bode plot of this, a log-log plot at low frequencies. So this is log frequency, and this is just magnitude of this transfer function. And at low frequencies, it would be H0. In this case, that would be 0 dB. And at high frequencies, it's inversely proportional to frequency. So a straight line on a log plot with a slope of minus 20 dB per decade. That's inverse proportion to frequency. All right? And then the asymptotes of this, where these meet, would be at the frequency omega naught, and we know there's some loss of 3 decibels at that frequency. So we've seen that stuff before. And we could look at the phase response if we wanted to as well, and it'll be 0 degrees at low frequencies and full 90 degrees at sufficiently high frequencies. So in filter terminology, this is called a low-pass filter. It passes the low frequencies and attenuates or tends to remove the high frequencies. So that's all pretty straightforward, pretty easy. In filter theory, one of the things is if you build a filter and you swap the locations of the capacitor and the resistor, you can turn what's a low-pass filter into a high-pass filter. So if I do that here, put the capacitor over there and take the output through this, by the same token, let this be the output, then here we would get H of S equals just the V out of S over V in of S, frequency domain stuff, then we take this thing, that impedance, divided by that plus the impedance of this guy, which is 1 over SC. And so this thing, we multiply top and bottom by SC. Now we're going to get SCR divided by 1 plus SCR. And this thing can be written as some kind of a H infinity, if we will, times S over omega naught divided by 1 plus S over omega naught, where again, the cutoff frequency is 1 over RC, but we should maybe call this one H infinity, the gain at real high frequencies. When S is much, much greater than omega naught, this term goes away and we get a high frequency gain, which is in this case approximately 1. So this is some H infinity, which is the gain magnitude of H as omega goes to infinity, and that's what that is, and of course in this example it's 1. And so this thing is just like the Bode plot that we had before, except for it does this. So this is 0 dB, this is log frequency going this way, this is omega 0, and now, and this is of course plus 20 dB per decade, I'm not going to write it down. So this thing passes high frequencies and it attenuates low frequencies, so this is called a high pass filter, okay? Filtering out the high frequencies of things. You can also see these things but directly from the circuit, by the way, and we'll talk more about this, or we'll do this in a lot of examples. If you go to high frequencies, the impedance of the capacitor looks like 0, looks like a short circuit. So at high frequencies, the input and the output are just connected, so the output's equal to the input, so that's what happens over here. And then at lower, as the frequency goes down, this looks more and more like an open circuit. So in the limit of 0 frequency, there is no gain. So this thing on a log plot is just going to minus infinity decibels, which is 0 on a linear scale. So that one's kind of easy, I guess. Here's a more interesting one, still not too hard, but interesting nonetheless. And this one involves 2 capacitors and 2 resistors. We remember that we said roots of the denominator of a transfer function are called poles, and we said roots of a numerator are called zeros. The circuit I'm going to show you now has both a pole and a 0 in interesting places. So let's put a resistor R1 and a capacitor C1 in parallel. And then down here we'll have a resistor to ground, and call it R2, in parallel with the capacitor C2, and we'll take the output across both of those. Now there's different ways of writing this thing. There's a lot of ways of doing this, and I'm not sure what's the easiest for you. One of the things that is handy is if you forget how to do things one way, you can always do it another way. One way would just be to write the parallel combination of these guys, make an impedance for both of them, and use the voltage divider formula. That ends up with a fair amount of algebra. Another way we could do this is just to kind of look at it for a while and see if we can figure out what goes on. Let me see if we can get away with that one. At low frequencies, the capacitors look like open circuits, right? So at low frequencies, this circuit just looks like the resistive divider with R1 here and R2. So at low frequencies, the DC gain, we'll call it H0, that's what we were calling it before, the DC gain should just be R2 divided by R1 plus R2 by voltage division. The capacitors are just open circuits. Okay, so that's some useful information. Even if we can't do any more, we've learned something about this circuit. That's the DC gain. Now, at very high frequencies, the capacitors look more and more like short circuits. So the parallel combination of these guys is 1 over R1 plus SC. That's 1 over the sum of the admittance or the conductance associated with the resistor plus the admittance associated with the capacitor. So I'll call it like 1 over, well, Y sub R plus Y sub C or something like that. And that's the Z associated with the first thing there. So that's how I got that. And I guess at this point I might as well keep going with this. Let's see, that's Z1, so we can write the whole thing this way. So there's a corresponding expression for the impedance of this thing in combination. So that's going to be 1 over R2 plus, this was C1, this is SC2. So now I can use my voltage divider. We'll come back to that trick, and I'll show you another way we could have extended that. But let's go on from here. So V out over V in here, if we use this thing, is Z2 divided by Z1 plus Z2 by the voltage divider formula that we started with. And I've got expressions for this. They're a little complicated, but maybe not too bad. I don't know whether I'm going to like this one or not. But let's do it. All right, so this is going to get us our answer. Z2 is 1 over, this is kind of a big mess. Kind of regretting having gone this way, but if I keep going, at least I'll get somewhere. SC2. So that is Z1, and that one is Z2. So that much works. So it looks kind of complicated. I don't know if I even want to say any more about this. This is an example of how the algebra can get complicated if we're not careful. But we can come back and check that. What I really should have done, I think, another way to do this is to go to high frequencies and make another voltage divider. At very high frequencies, the resistors look like, compared to the capacitors, the resistors look almost like open circuits at a given frequency. At high frequencies, this whole circuit looks pretty much like C1 and C2, okay? Because the parallel combinations of these are completely dominated by the capacitors, and the Z's just look like the inverses of the capacitors. Now the problem with this is then H infinity. We have to be a little careful because these are capacitances. They're inversely proportional to the resistances. So the voltage divider formula, another way I could have written it is Y1 divided by Y1 plus Y2. I didn't tell you that, but it's true. That's going to give me SC1 divided by SC1 plus SC2. And of course the S's cancel. So this is what I was after all along. I already knew that, but I took some extra steps to get there. So that is what we would call H infinity. So this actually, now I need one more thing and then we could make a Bode plot. I need to find, and there is a trick which I'm going to tell you right now. If you have a circuit in which you have a single capacitor, then the frequency of the pole associated with that circuit is 1 over the product of the capacitance times the resistance seen by that capacitor. And that's a resistance that we would find with the voltage sources short-circuited, or if we had current sources, they'd be open-circuited. Well, it looks like we don't have just one capacitor, but if I short-circuit this guy temporarily, just so we can talk about it, look, C1 and C2 are now in parallel. They may not look like it, but they are. So C1 plus C2 have a resistance in parallel with them. I say they see a resistance of R1 in parallel with R2. There's a formula for that, but it's straightforward, right? And so this pole frequency associated with this guy is at 1 over C1 plus C2 onto whatever this is, the parallel combination of R1 and R2. So that's just a trick, but it's so handy that it's a good trick to know, all right? And so sometimes we can do a full, more complicated version of that, but this is a way that will get you there. So here's the deal. I just don't like that form, so I'm going to go ahead and erase it. You can check against it and see if my final result works with that. Here's what I wanted to say. At low frequencies, the gain of this thing is at R2 divided by R1 plus R2. That was my H0. At high frequencies, the gain is either higher or lower depending on the size of H infinity. It could have been higher or lower. I'm going to draw it as if it's lower. All right? So this is my H infinity, which we just said was C1 divided by C1 plus C2. And if I can now figure out where the pole is the place where this thing breaks down. So in this case, the pole is here, and this thing goes down inversely proportional to frequency until it meets this guy. So this is how we do the Bode plot for this guy. So this is the omega 0, the frequency of the pole, and we haven't actually done the expression yet for the frequency of the 0. Let me show you how to do that one real quick. We've actually got all we need. One of the things that's interesting about this is that there are really 4 quantities we need to evaluate to do this transfer function. H0, H infinity, omega 0. That's unfortunate. The omega P, which I'll say is the frequency associated with the pole, and omega Z, the frequency associated with the 0. We need one of those, and I can show this is an inverse proportionality, and it shows me right away that the ratio of H0, the DC gain, to the gain at high frequencies is equal to the ratio of the frequency associated with the 0 to the frequency associated with the pole. Since I was easily able to figure out what H0 was and H infinity was, and if I can find out how to find one or the other of these, then the last one I can get from this formula. So it either is a way of checking your work, or it's a way of, if you don't know how to do one of these things and you knew 3 of them, you can find the other one from that. This transfer function, which I've actually erased, has 1 0 and 1 pole. It's of the form either H0 onto 1 plus S over omega Z to 1 plus S over omega P, the 0 and the pole frequencies. And if you go through all of these things, you can say that this can also be written as, and I'll let you go through and easily show this. I'm just going to multiply through and basically use this. And that can be written as this form. And let's just check these things. If S is much less than 1, so this is the H of S for this circuit. If S goes to 0 at very low frequencies, this whole fraction turns out to be 1, and the whole product is equal to H0, the DC gain. If S is very much larger than either one of these things, then this fraction evaluates out to 1 in this form, and this H infinity is the gain at high frequencies. And then if you work through, that's consistent with this. All right, I'm going to show you one more thing about this, is given this circuit, well, remember it originally had an input. I'll show you a trick that you can always use to find the frequency of the 0 of a circuit. It's a little bit of, basically, you say the admittance of this guy is this. So the question is, at what value of S would this thing give 0 output? Okay. Well, if C2 somehow went to infinity, that would work, but that wouldn't always give us 0. But if somehow this thing could be evaluated so that there was no transmission through it, so the parallel combination of this guy is 1 over R1 plus the admittance of the capacitor, C1. If somehow that whole thing was equal to 0, then there would be no output, no matter what the input was. Okay? So if I do that and solve for the value of S required to give us the 0 output, it will eventually solve for the value of this. That says S sub Z times C1 is equal to minus 1 over R1, from which I can get S sub Z equals minus 1 over R1 C1. And that's the location of the 0. So when we go back through this whole thing and write this in either of these forms, and I'll let you go back, you can run the thing back and look, and this will be the frequency at which the numerator goes to 0 of this thing, which is the value of the 0. So there's a lot of good tricks in here that you can use. This circuit is actually pretty interesting. You can use this circuit, and you may have seen this before somewhere, maybe with an op-amp or something like that in there. Things like this, in this example, this could be used like the low frequencies or the bass. So maybe this was a circuit that was raising the bass, and so this is like a tone control, or it could have been that this was lowering the high frequencies, the treble. And maybe you'll see somewhere a thing that is a bass control where you can swap around between several versions of this thing. You can increase this and get an increase in the low frequencies, a bass boost, or you can change the circuit around so that this thing attenuates the low frequencies. If it's in this attenuation form, this is the omega 0, and this is the omega of the associated with the pole. So you get two different transfer functions. Anyway, this thing can be used as a base control or as a treble control, so it's kind of a handy circuit that gets used in a lot of applications.